In this screencast, we're going to go over some common sample problems that you might see on the acids and base tests. So the first question has to do with actually concentration. What is the concentration of a solution with 2.3 moles of solute in 1,350 milliliters of solvent? Well, when we look at concentration, what we're actually talking about is molarity. And molarity is the number of moles divided by the total volume there. So moles divided by volume. And that's what we just need to do here. We have 2.3 moles of a solute, and it's divided by liters. Our problem gives us milliliters, but it's actually really easy to convert from milliliters to liters. It's metric, so there are 1,000 milliliters in every liter. What you end up doing is moving the decimal 3 places to the left. So it's 2.3 moles divided by 1.35 liters, and we get 1.7 molar. Capital M stands for molarity or molar, and it means moles per liter. So let's try some pH problems. The pH of a solution is 3. What is the pOH? Well, we have to remember that pH plus pOH will always equal 14. So if we have a pH of 3, the pOH when added to 3 must equal 14. So what we can do here is just take 14, subtract 3, and we find the answer is 11. The pOH is 11. The concentration of hydronium is 4.5 times 10 to the negative 4th. What is the pH? Hydronium, or H3O+, is essentially the same as H+, just hydrogen ion, when we talk about acids and bases. It's really just that one is also attached to a water. So for our purposes, when we ask for hydronium or hydrogen ion concentration or pH, we're really talking about the same thing. So we have an equation for this. The pH is equal to the negative log times the concentration of hydrogen. So all we really have to do is plug in our number. To find the pH, we type in negative, the actual negative symbol on your calculator, not the minus sign, but the negative symbol, log, and then type in 4.5. To type in the times 10, it's best to use the EE button, the 2 capital E's, and then negative 4. And once you type that in, what you'll find is the answer is 3.35. So that tells us the pH is 3.35. If the concentration of hydroxide ion is 2.3 times 10 to the negative 11, what is the pH of the solution? Well, this is actually going to take 2 steps. We have an equation from a previous problem that said that pH was equal to the negative log times the concentration of hydrogen. Well, the same is actually true for hydroxide, OH. The pOH is equal to the negative log of the OH concentration. So that's what we'll do. We'll just plug that in similar way. So pOH is equal to the negative log times the concentration of OH, 2.3 times 10 to the negative 11. And that will give us the pOH of 10.6. Now, in the earlier problem, we also know that pH plus pOH will always equal 14. So what we can do here is take 14, subtract 10.6, which is the pOH, and that leaves us with 3.4 for the pH. So this is an acidic solution with a pH of 3.4. If the pH is 11.2, what is the concentration? Well, now we're going backwards. We're no longer going from concentration to pH, we're going from pH to concentration, which means that algebraically we have to move our equation around. And when you do that, what you get is that the concentration of hydrogen ions is equal to the antilog of the negative pH. This has just been rearranged algebraically. So when you type this into your calculator, you type in antilog, which usually is the second button and the log button, and then you type in the negative symbol, 11.2, and you'll get that the concentration is 6.3 times 10 to the negative 12. Let's look a little bit more closely at acids and bases. A strong acid and a strong base always produce what 2 things? Well, as long as they're strong, they'll always make a salt and water. A salt, not NaCl necessarily table salt, but a type of salt. Now consider the following equation. Hydrochloric acid and acetate yield acetic acid and a chloride ion. Okay? Now a question is the acid Arrhenius, Bronsted-Lowry, or both? Well, the acid in our equation is the hydrochloric acid, HCl, and it's going to donate its proton to the acetate to create acetic acid. But I don't see any hydronium ions or hydroxide ions or hydrogen ions, which tells me that it's not Arrhenius. It's just Bronsted-Lowry. The Bronsted-Lowry acids and bases will donate or accept protons, and Arrhenius will produce either hydronium hydroxide or hydrogen ions, and I don't see this, so it's not Arrhenius. Now, what is the conjugate acid of our equation? Well, we know that the hydrochloric acid is going to have a conjugate base. So hydrochloric acid is the acid. So when we follow the chlorine, we find our conjugate base. On the other hand, then the thing that's been added to the acid must be the base. The acetate ion is the base, and its conjugate is the conjugate acid. So the CH3COOH, or the acetic acid, is the conjugate acid. Let's look at equivalence point. For the following situations, tell me if the equivalence point is neutral, acidic, or basic. We have a strong acid and a strong base. The equivalence point will be neutral. If we have a weak acid and a strong base, the equivalence point will be basic. And if we have a weak base and a strong acid, the equivalence point will be acidic. Now here is a titration problem. Titration problems, in my mind, have about 4 steps. You could argue that these only have something like 3 steps because you can do some of the dimensional analysis in 1 step instead of 2. But for our purposes, I'm going to break it down into 2 steps. So our situation is that we have 25 milliliters of a 0.05 molar barium hydroxide solution that's been neutralized with 40 milliliters of nitric acid. And we want to ultimately determine the concentration of the acid. It's unknown what the concentration is. So we have 3 pieces of information. And one of the first things we're going to need to do is actually write a balanced chemical equation for the reaction. We need to know at some point the mole ratio, so we might as well balance it first. So when we balance the equation, we get barium hydroxide plus 2 nitric acids yield barium nitrate and water, 2 waters. And the 2 in front of the nitric acid and the water are going to make sure that our equation is balanced. And what you see is since these are both a strong acid and a strong base, we get a salt, the barium nitrate, and we get water. Okay, now we're ready for the next part. Now this is a part that I break down into 3 steps, but on a test I would ask you to just tell me the concentration of the acid. So these next steps, you would need to understand how to get there. So in order to go from our known concentration, which is the barium hydroxide we know is 0.05 molar, to a concentration of the unknown, the nitric acid, we're going to have to get down to some moles here. So we can get to mole ratio, do the mole island thing. So the next step we need to do is calculate the moles of barium hydroxide. We have concentration, we have volume, so we can figure out moles. So what we do is we take the concentration of 0.05 moles of barium hydroxide, and we know that it's moles per liter. Now we also know how many liters we have of the barium hydroxide that's been used to neutralize. That was 25 milliliters, so I'm going to write this as liters, and just put it over 1 so that I remember that this is just part of my equation here. So now our liters will cancel and our answer will be in moles. So we now know how many moles of barium hydroxide were used in this reaction, 0.00125 moles. So the next thing we need to do is go from moles of barium hydroxide to moles of nitric acid. So we need to find the moles of nitric acid. And the way we do this is we take the moles of barium hydroxide and we are going to, just put that over 1, use the mole ratio to find out how many moles of nitric acid we have. So I know that I need to put moles of barium hydroxide on the bottom in order to cancel with dimensional analysis. I want to get to moles of nitric acid. Then I look at my equation. Barium hydroxide has no number in front of it, so that tells me that I need to put a 1 in my problem. Nitric acid has a 2 in front of it, so I need to put a 2 in front of the moles of nitric acid. Now my moles of barium cancel, and I can find the moles of nitric acid. So I have twice as many, 0.0025 moles of nitric acid. Now my last step is to calculate the concentration of the nitric acid. Concentration, or molarity, is moles per liter. This was the first problem we did in this video. So I take the number of moles, and I divide by the amount that I used, which was 40 milliliters. Remember to convert milliliters into liters. Then, we've got the molarity of nitric acid, 0.0625 molar nitric acid.